over-the-horizon radars as well. So they are looking for uncooperative HF transmitters, for example, those that violate frequency license and without knowledge of the ionosphere, and they need tens of kilometers. Yeah, they have a tens of kilometer positioning errors. And as you see from the language that these users are using, they say it's a short-range catastrophe. So if you look at the language, a killer catastrophe. So I think the community is ready for a new means of monitoring ionosphere in all its glorious dynamics. HF communication still really important, considered to be a high reliability, high availability, low latency messaging and voice communications. One of the prominent users of that ionospheric HF communications is business transactions that are almost instant, unlike other ways of communicating. Rescue, covert missions, various military cooperative, like soldier to headquarters, ship to ship communications. Aviation, ground dispatcher to pilot safety messages goes through HF, especially on those transpolar flights where HF is basically the only way of communicating. And of course, ham radio enthusiasts are one of the popular. Okay. All right, so RION, Realistic Ionosphere, is ISWI instrument, as they call it. So we joined that ISWI in 2017. This is United Nations Office for Outer Space Affairs. So it's a United Nations project with a strong NASA influence. So NASA bring the need for the objectives to be about space weather science rather than applications. So the ISWI is basically a scientific project. And they, of course, do the capacity building and outreach, as many of the United Nations projects do. In 2017, we registered all available ionosonde product and services. I was not sure for this audience. Shall I talk about ionosondes a little bit? Anyway, this is the...
Yes, please.
All right.
Yeah.
All right. This is the historical reference of how ionosondes appeared. You know, in our field, there are two Nobel Prizes, Giuliano Marconi and Sir Appleton got them. Marconi, of course, did the first transatlantic radio communications using the high frequency, and Appleton explained it. Then the most extraordinarily, the world goes wireless in 1922 when the broadcasting began. 1925, that's when the first ionosondes appear, and the reason why it's plural, not just ionosonde, first ionosonde, is because there were two of them built practically within the same year, 1925, in the United States and UK. UK first, United States second. So these were the systems to probe and prove that indeed the signal reflects from some magic mirror in the sky, and not traveling along the surface, because most of the people at that time thought it was traveling along the surface. But yes, so that was the technique that was able to indicate that it actually and measure the height of reflection. Yeah, that was the glorious days that made geophysics treat ionosphere as the most exciting object to study. So then World War II, that was a radar era. Most of the ionosonde folks just moved to the radar community, and they came back after the war to establish an International Geophysical Year. 150 ionosondes operated then. And then we had space. The world went to space most extraordinarily. So, and then there was ISR era, the incoherent scatter radar appearing in the 50s, late 50s, actually, I would say. But they became overwhelmingly popular and shadowed the world dominated by ionosondes. And then GPS came. That was the second attempt to replace everything previously known to probe ionosphere with the tomography and total electron content measurements. And about the 1990s is when the proclamation that HF is dead started. And this is not true, apparently, as we will show today, probably also. But there are certainly applications that require HF, and it's actually growing interest to HF. Then radio occultation error became later, and now I would think it's traveling ionospheric disturbance error. And last week it was sporadic layer error. Okay. All right, let me continue on the path. So in 2018, RION, which used to be a purely ionosonde system, data system, added GNSS services in something that we started to call Gambit project, global assimilative model of bottom side ionosphere with top side extension. So it's a Gambit. We in the core of the Gambit, there is a model called IRTEM. It's an IRI-based real-time assimilative model. Its current version includes only bottom side ionosphere, but we have ideas how to extend it to other resources so that we can cover a greater altitude range with this assimilative model. And at that time, in 2018, we added VTAC data from Madrigal data system and IGS, which is International GNSS service. So with Gambit Explorer, which you can download on this link, and with the warning that it may become addictive. Yeah, you watch this global maps in their progression in animations. That's really entertaining. Okay, so that VTAC is now, there are connections, online connections to Madrigal data collections at Haystack Observatory in the United States. And there is also IGS data connection to University of Warmia and Missouri Coordination Center in Olsztyn, Poland. So this allows us certain things. In particular, we started with this cooperation project called Data Fusion, and the first GNSS GIRO is ionosonde, GNSS is GNSS. Data Fusion products started to appear, and there are two of them that we will mention today. There is a comparative anomaly maps, VTAC versus peak density. Let me speak about anomaly a little bit and effective slab thickness. Anomaly is the first time I mentioned that word. We have a special meaning on that, so maybe very quickly about terminology. It's not really consistent, I have to admit, just watching the literature. I think when you talk about tech in time, whatever it changes, how it is changing in time, then the terminology is ROT, the rate of tech, or there's also index, and that has to do with the derivative in time. When you talk about spatial gradients, the terminology is usually DTAG, but it's ambiguous, actually. I would not use that notation, which is a gradient, is better. There is also detrended tag when you process it to remove the perturbation component. Well, not remove the slow variation and keep the perturbation component, so that DTAG would be used for that. And we are using tech anomaly. Anomaly is weather minus climate. So how different is current ionosphere from its expected behavior, right? So it can be more than usual or maybe less than usual, and we use the notation of delta tech. And here's an example that I built using the VTAC data from a Madrigal, and you see this is not tech. This is anomaly of tech, all right? and it's vertical too. Yeah. So you see everything red means it's unusually high total content. So what you see here on screen is actually not fountain, not the Appleton anomaly. It's the super fountain, which is greater than usual. And when you see blue shades of color in this, that means really major loss of plasma. The plasma disappears. Yeah, that would be like 75% loss. That's a lot. Okay, so
Ivan,
that's
can I make a comment?
Go ahead.
Yeah, even the bubbles we can see right here over South America during the
Yeah.
nighttime,
Yeah.
plasma bubbles.
Yeah. Georgios defended his thesis on plasma bubbles. Of course, he's yeah, you can see that. That's right. And we don't see much in Africa, right? Yeah, that's the one of the most interesting thing because it's a low latitude, and there's not much available in the low latitude really, except for a beautiful coverage in the South American sector. American sector is great there. Okay, here's the comparison that I mentioned to you. So we are putting two very different instruments, GNSS receivers and ionosones on the same chart. This is anomaly, right? So how different is ionosphere from its expected behavior? So the surface color is GNSS, and we have about 6,400 GNSS sites that contributed to this chart. Okay, someone is happy to see GNSS. Right, I'm also excited about this capability of, this is a super fountain. You can see this is the plasma enhancement, very, very peculiar shape enhancement that a storm effect. Okay, and the colored dots are peak density deviation, okay, anomaly, right? So you see, we agree most of the time, but sometimes we do not agree, which is curious, right? For example, here over the Europe. Yeah, so that means that total electron content and peak density do not necessarily behave similarly. It's a good question because everybody talks about assimilating tech, and it's not easy. Okay, from these measurements, which are individual dots, right? Okay, there are many of them, but still they are dots. The next step would be to go to a global mapping. There are two techniques I used separately, differently, for GIRO data and for GNSS data. Our approach is IRTEM, it's a assimilative model, and we work with anomaly, not with the variables themselves. So we compute from the observation at each site of GIRO, at each observatory where the ionosonde is operating, we compute weather minus climate anomalies. How different is that particular observatory? We use IRI as the underlying model for the quiet time and just compute the difference, and then we interpolate these anomalies to the global scale. And what we do when the distance increases from the site where the anomaly is observed, we gradually reduce that delta to zero. So essentially, we go back to the climate quiet time over the areas where we don't know what's happening because there are no sensor. Our approach to that interpolation is neural processing to avoid sharp discontinuities, which is different from other systems that assume particular spline or harmonics or I don't know, kriging, or all these things. They have to assume certain function. And neural processing is different. We don't have time today to explain it, but if you're interested, I can get a separate presentation on that technique. And then this global anomaly map is applied to the IRI, and we get the weather specification. And it can be done pretty quickly, within 7-8 minutes from the measurement. Yeah. And by the way, what you see on screen, these GIMs and IRTM is probably the only resources that are available in near real time. Everything spacecraft is, of course, fancy and useful and revealing, but it takes time for the observation made by a spacecraft sensor to get downlink to some ground center. And these delays are just too large, too large for the weather monitoring. Jim, I'm not the expert on GIMs. I know that the bias has to be estimated before this computation is done of VTech from this LandTech. I know that they do not work with anomalies. They just fit the global basic function to the whole collection of these thousands and thousands of VTech points. Okay, so let me skip this one. It's reiteration that we are working from deviations, from the anomalies, not with the FOF2 or HMF2 itself. The need to capture the geophysics of sun activity, mode migration, because the poles are migrating, right? The magnetic field, seasonal specifics. You don't have, with this assimilative model, you don't need to reflect them. You don't need to learn them. You need to memorize them. IRI does it for you, and IRI does it very well. What you do, you smoothly transform the IRI to match the observation, okay? I call this process morphing. And there's a picture of like morphing. You see that's a smoothly transforming the underline. It's classical gray box approach. If you're into white box, black box, this is gray box. It's a physics-informed assimilative modeling. So what we do, here's the example. We need a 3D specification for many applications like ray tracing and other things. And we just, IRTEM uses 4 different parameters of the vertical profile of ionizations. Assimilation is going in the 2D, not 3D, but 2D. Okay, and here's the example of how the resulting global map of the IRTEM works. And let me mention something else. IRTEM is a significantly 4 DDA. And there is something that I call time to space translation. Let me explain. So most of the popular assimilation techniques nowadays are 3 DDA, meaning that they look at latest data, right? Whatever latest is available, and they do 3D in space of plasma distribution, right? We are doing 4 DDA. That means that previous data history is analyzed. There's nice studies that indicate that if you look at previous state of the system and current state of the system at the update step, you can catch the dynamics better, and this 4 DDA are considered to be superior if you can go back one step. IRTEM is a 4 DDA with 24-hour history analysis. Not 15 minutes, not 5 minutes, 24 hours. So one computation, we look at 1 day of the observations. And again, we are looking at deviations. And not only that, we compute diurnal harmonics. 4-hour, 8-hour, 12-hour harmonics of these deviations. So we treat the ionosphere like its anomaly it has a wavy structure, wave-like anomaly. So that, and each harmonic of that expansion is analyzed separately during the expansion of this correction found at the observatories. And the simple argument for you is that suppose you're sitting somewhere like Millstone Hill, right? You have a digital there, and you observe an 8-hour harmonic anomaly. That means that you see that the ionosphere goes up and down slowly with the 8-hour. That is, of course, planetary scale wave-like anomaly in space. So that's how you go from observation in time to observation in space. So IRTEM has that capability of extrapolating from the individual dots to the global picture individually for each harmonic, and the covariance ellipses are different for depending on how large is that wave. Here's a single site, so to illustrate, right, what one computation done for this moment of time, here it is, looks 24 hours before it. Everything blue here is the measurement by the ionosonde in Lowell. This is Hawaii, United States. And you see this is like, there's a little bit of gray color used for low confidence outer scaling. It's all automatic. The model fit of IRTAB is the smooth golden and red line. So golden is local, red is global. And they coincide very nicely because there's nothing else around Hawaii. It's an island. So, and the green line is the quiet time behavior. So you can see in this particular example, this is HMF2. It's a peak height. You see a magnificent event of the large scale 4-hour harmonic wavy behavior because of the traveling disturbance. Okay, so there's another way from a single point, 24-hour. Let us look at the animated history during the storm time. And I was trained to think about negative phase and positive phase of the storms, right, in progress. And I'm looking at this picture and I don't know what is happening. It's negative and positive at the same time. So that is something that we as a community may be able to reason about why there is immediately extra plasma and loss of plasma happening at the same time. And this is not small. It's a 75%. Yeah, 75% depletion and 75% enhancement of plasma during this storm time. Okay, so how do we cooperate now with GNSS and GIRO together? One way, and this work, and Jonna, can you remind me how much time do I have? Shall I be kind of wrapping up?
You could do like 12 more minutes if you want.
All right, okay. All right, I'll stop because I thought it was like 40 minutes, 45 minutes. All right, so cooperation, how do we cooperate? I am currently remaining skeptic that we can assimilate tech. There are some schools, Tamara Gulaeva, of course, and Alessio Pinalberi from Italy. They look at the anomaly of VTEC, and they say, if anomaly is visible in VTEC, we can kind of assume that it's gonna be driven by the density around peak height. So the peak density. So whatever anomaly is visible in VTEC, they say the same anomaly will be visible in the peak density. I am still a skeptic. Yeah, there is at least one very nice model called Gypsy that recognized that if you allow GNSS into your assimilative model, right, you will face the 6,000 versus 60 problem. If you remember the chart a few slides back, we have only 60 ionosones and we have 600 receivers. They will drive the assimilation. The ionosones will be kind of forgotten in this scenario. And we are not quite sure yet that the tech and peak density are behave in like co-vary together. In fact, I see our research group from the IRI workshop is here, and we are studying, trying to understand how much is the contribution above topside topside ionosphere, plasmasphere include, how much of this deviation is driven, let me say it again, how much the deviation of tech is driven by the plasma above the peak, which is unrelated, right? So above the peak, and well, Bushra is saying it's 40%, 60% sometimes, even more. So we are remaining skeptical about this. So this work is a different one. Data fusion project, we just combine NMF2 and FVTech measurements together to reason about slab thickness. Unfortunately, time is running out. Slab thickness is the indication how stretched in the vertical dimension or how compressed in the vertical dimension the ionosphere is. And this is an example of the climatology, quiet time. It's some November, and you see this is the nighttime, and there is certainly, you can see that the ionosphere is compressed along the equator. There is a little bit of expansion happening at the anomalies, and there is a very significant stretching happening in the dawn times because the sun is already ionizing plasmasphere and not ionosphere, so that's why the profile appears to be stretched out. Well, the anomaly, interestingly, anomaly map, if you look at that, that is probably a Persian rug. It's all colors. Again, it's a storm time, and you see positive, negative effects happening simultaneously. So it's really a revealing capability that a realistic ionosphere will give us to study these storm effects. So what is happening here? We don't know, right? For some reason, ionosphere can be compressed and stretched at the same time. This is just one time, right? The whole globe. What do? We compared that slab thickness to a MUF, maximum usable frequency. That computation does not use VTech. It's pure bottom side, right? Now, the slab thickness includes GNSS, right? So you see whatever is like blue here is red here, so they're working in the opposite, and whatever blue is here is kind of reddish here, and you can find these correspondences nicely here and here. So definitely combining our forces between GIRO and GNSS can give us a capability of sensing MUF, maximum usable frequency, which is, of course, driving all the HF communication needs, civil aviation, ship-to-ship correspond messaging, things like that. And look, this is 50% deviation here. This is 75% deviation there. So it's a more sensitive system. Okay, 2026, Giorgio joined our system, Realistic Ionosphere project. New GNSS products will be available soon. Soon we will have VTech, we will have oops, I stand corrected. Yeah, I should have used the operator here myself. Okay, so differential in space, differential in time, VTech anomaly, weather minus climate, DIX, disturbance ionosphere, disturbed ionosphere indicator, something that Giorgio invented for his doctoral research. Slab thickness, it's anomaly. It's all gonna be soon, really soon available as a part of the realistic ionosphere in cooperation of two communities. And in future, we'll start thinking about assimilating cosmic data using did I say electric light orchestra? No, elastic linear optimization technique. For cosmic, near real time may not be possible because of delay. There's at least 1 hour delay to the ground station, and then it has to make through the various systems there. So I would say near real time may not be possible with cosmic. But anyway, I think it's at least a good thing. I'll have to skip this slide as that explains how different is the NECTAR, which we currently use. NECTAR is a assimilative technique in IRTM from ELO that will be used for moving platforms. Let me just mention that this is our upcoming chart of all the sensors available in Lowell, Massachusetts. Soon, some of them are soon, some a little bit later. So these are ionosones of GIRO here. There's a permanent GNSS receiver stations. They're practically, yeah, Georgia is already doing that, but we will really build a nice data system for his computations. And then cosmic 2 occultations, cosmic 1 also will happen for historical data, will happen soon. So this is just a diagram to impress you with the number of different databases we operate. There are 9 of them that we have. And let me quickly run through the various products that we didn't talk yet. Raytrix, Skylight, TID Explorer, and Ionospheric Disturbance Indicator. Okay, let me start with Raytrix. Raytrix is just a way of computing how HF signal propagates this the ionospheric channel. So we today have decided on the use of the composite quasi-parabolic representation of the ionosphere, and we have a GPU implementation of the code, and we spend a fraction of second, a small fraction of second to get this computation of the oblique ionogram, how many paths through the ionosphere from the transmitter to receiver exist on the given a given link, okay, which is about 1,200 kilometers. Okay, there's a HR 2006 ray tracing, which is a high quality stepping ray tracer, will be available. So you see, we support various Spitzer effect. It's called Spitzer effect. This is the result why people are telling us it's a short-range catastrophe. That's because the propagation is very strange, and this code can cover it, can replicate it. Doppler sky mapping. Digizone illuminates the whole sky, watches for the reflections coming back from the disturbances, small-scale disturbances, which are large enough for the HF to reflect back. So, and you see, we see something in the blue, it means something approaches us from this direction. It's Doppler. And red, something goes away. So this is Boa Vista in Brazil. So this is an example of the ionosphere traveling as a single structure in the west-east direction. This is a bubble, right? That is a bubble. So sky maps were proven instrumental in determining some of the very interesting plasma cannon effects. So you see, this is Doppler. Negative Doppler means plasma moves away from us along the magnetic field line. This is magnetic field line, and this is Gakona. The nearby HARP facility is hitting the ionosphere, creating supra-relativistic electron beams, and these are moving away with increasing velocity. That is a plasma cannon. Yeah, that's why the there is a publication. It's a public knowledge. Okay, and there's this heating is responsible for forming the artificial layer like this. Oh, they stop heating, the layer disappears. Here's that's the layer which is moving downward, and the upper portion we don't see except through this sky mapping. TID is important. Ionosphere goes up and down, disturbing the quality. We are very, very powerful in that respect. Sensitivity is great. We see 5% of underlying density modulations. Even when we see 40% underlying density modulation, GNSS sees good 10% of total electron content modulation. So we are significantly more sensitive to see how which way the plasma moves. Well, this is okay. No time to explain that chart. And TID is, of course, I think this is basically my last slide. It requires significant effort of the artificial intelligence to figure out the signal path through the ionosphere in order to compute the TID direction, amplitude, wave length, and velocity of propagation. So that information is good for the forecasting impact of TIDs on operational system. If you install them and in northern territories, you can catch the auroral oval brightening and associated TIDs with this technique. Okay, and this is my last slide, ionospheric disturbance indicator. So with these ionizon techniques, we can detect presence of the small-scale disturbances. These are important because they are responsible for the scintillation effects. Spread depth in ionograms. Again, this is definitely low latitude Brazilian station. I cut which one, but certainly when you see this range spread so high, these are bubbles because the signal is trapped into that bubble structure, which is like elongated, and it spends more time trapped within this bubble going forward, backward before reflecting. So that would be a classical way of determining presence of that disturbance. And then again, the sky maps will give us a wide echo cloud when the disturbances are present, because if there is no disturbance and the ionosphere is smooth, the sky map will have just one single point in the middle, nothing else. This is a clear indication that the plasma is disturbed. And we have something called directograms. This is also, I think it's a Hikamarka. And then you see how the bubbles are traveling across the station in this type of the measurement by the ionosondes. Let me stop here. I apologize. I had to cut shorter my presentation, but it is available by request. Maybe Jonna, you can send it to send it, place it, publish it somewhere else. So just in case there are additional questions, let me stop here and thank you all for your attention.
Yeah, wow. That was a big talk, Dr. Ivan. This is really cool stuff you showed. I think you need like, no, we hold this meeting 10 times a year. I mean, 10 times, right? In a year. And we should invite you for the whole 10 times. That would not be enough.
Right. I can talk about this plasma cannon for a while. Yeah.
Yeah.
This is really neat. This one, and there was an optical camera watching this plasma flying away, and our velocity and their velocities are in agreement. Yeah, so that is good. Yeah,
And we're going to definitely invite you again to maybe focus on one at a time, so that particularly you mentioned TIDs and you already talk a little bit, and then there's so many topics here that could take a whole year to analyze correctly or with detail. So I think you are owing us more talks here on this platform.
all right, all right. Sure,
Yeah.
I'll be delighted. Yeah, to come back
Yeah.
sometime.
Excellent. Thank you so very much for this excellent talk, Professor Ivan and Galkin. And I want to open it the floor for the questions. If there is any questions, please feel free to ask your questions. We have like 5 minutes, but we can go a little bit above. Sometimes we go above for like 10 minutes, so it's okay. So if you have questions, you can ask. Let me see if there is any question in the chats. just raise your hand or just unpause yourself and ask your question. I have Bruno's question. Bruno, you can talk. Come on, let's go.
Yes, good evening, Dr. Jenna. Can you hear me?
Yes, yes. Loud and clear.
Okay, that's good. Thank you, Prof, for the presentation. So my first question was on when you're doing the combination using the GNSS, uh, is there an issue, especially over Africa, where we have stations, but the data is not continuous throughout the whole year? Does it affect the combinations, especially when we have the storms coming in? Then the second question was about the optimization. Is it that if we're okay, I think you can that the slide after this that shows Africa.
Which one? This one
There
is
was
after.
a slide. There is another one that had. There is one that had like showing all the networks.
All the networks. Oh, this one, right?
Yes. Yeah, that one. So if we look at Africa, you see we have like GNSS stations of like in a line. So do you have to do some optimizations to know that I can select some of these because literally they're on the same longitude and or latitude, or that does not affect in the combinations? Thank you.
Sure. Let me talk about GNSS first. The coverage is best. They have, arguably, they have like 40,000 receivers, right? About 7,000, maybe 8,000 receivers are available in public domain, but there are gaps. Oceans, not only Africa, oceans are gaps, right? There's a big blank. So what they do, one of the first steps when the GIMs are built is to pick up those representative stations whose data quality is good, whose the bias is well calibrated, maybe. So that selection is out of 6,000, maybe 300. So that is a complicated operation to make sure that the data are subset correctly. And then when there is no data, right, like in Africa or oceans, the only argument that I am aware of is smoothness. There should not be a strange interpolation effects across no coverage data. They should not, right? And how it is done, it's regularization. If you heard these expressions before, that is an operation that ensures that the interpolation is smooth and there is no what they call rinning. If you heard that expression, polynomial rinning. So if you don't clip the data, right, to a particular value, and you're using polynomials to represent it, splines or polynomials, they may start oscillating over the no data area. So what do? You put artificial points, they call it phantom points, to keep the interpolation from rinning. Where they're coming from, they are usually transformed along the same line of the modified deep angle. So you're assuming that whatever was happening an hour ago, they just extrapolate. In the past, that's how IRI was built, using phantom points. Otherwise, it would be unreasonably oscillating solutions there. Now, we have a great expert on the team. Georgia, would you like to comment? Because you have your own technique for the GIMs. How do you consider interpolations over no
Yeah,
data?
in these cases, it's very common in the community to define some grid based maps from the GNSS observations. For example, the Madrigal TC maps, if I'm not wrong, they define a grid of 1 by 1 degrees in latitude and longitude, and everything falling inside these cells, they are averaged. So this is a way of not interpolating but binding the observations, the GNSS observations, especially the TC, calibrated TC. Because if you are verticalizing it, you have to define where's the grid, where's the point into the grid's reference. So this binding technique is more acceptable. And most of the papers doesn't describe it as interpolation, but as binding. There are some options for interpolating the BARNet observations, but this is not very well accepted into the community. In this case of the anomaly maps that Ivan showed, I think Bruno's question is about the baseline for the differences, right, between the VTAC and ionosonde data. I think, even if I'm not wrong, the baseline, it's not the properly the ionosonde measurements, but the IR10, right?
The baseline for anomaly computation is IRI, quiet
Right.
time.
Okay.
Yeah.
Okay.
And then the measurements are compared to IRI quiet
Mhm.
time,
Mm-hmm.
and they are then extrapolated. Yeah.
Okay. So the
So
baseline, the area for the baseline, is considering everything that is falling inside the same grid for the GNSS TC measurements. Am I right?
right. Yeah.
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 Okay. Yeah.
So,
That's it.
Dr. Avon, I think there is a question that I was thinking about when you show the positive and negative some variation. How often do you see that? And could it be because most of these negative, positive, the video I saw maybe where there is no real data and interpolations that we are talking about
Yeah.
now are also a kind of instrumentation, I mean, instrumental to those things that one want to look carefully.
Yeah, John, a very good question, because I was questioned about it. As you see in this example, right, the anomaly map, there is extrapolation. Look at that. It's just extrapolates so large, but not always, right? It has its own life. It seems like this extrapolation is not a simple one. Because it's a extrapolation which is based on the underlying harmonics detected in the behavior of the ionosphere. So sometimes what we see in time, we kind of assume that the anomaly, right, will be expanded outside. And the first time I received that image, there was like, this is Ascension Island. You see my pointer? Right, this
Yes.
is Ascension Island. And apparently along the same motive, the extrapolation was allowed because it was the system detected presence of the harmonic of the, I believe, 8-hour harmonic of the big wave, and that resulted in a very interesting red spot in the middle of Africa. And I called it red spot over Africa. And I was questioned how real it is. And we are not ready to answer these questions. Bruno, dear Bruno, you're there. Yeah, so we are not ready. How can we? We need independent measurement, right? We need CONGA
Yeah.
for
Yeah.
as a minimum, right? But
As
we
a
need
minimum.
we need some other ways of really answering these important questions. Because then we can do the. I would be interested. Join me if you're interested too, to study that capability of IRTM to predict ionosphere in space, not in time. In time, it's miserable, right? A couple of hours and 50% of advantage is gone. Even 1 hour, 50. And so the old data is really not helpful. But in space, we are claiming that in space, IRTM is doing an interesting job. Yeah, maybe quite real. As for the GNSS, that's even more interesting because you see there are certain things which we have no idea because there were no measurements, and there's one island somewhere, French island, and it has a GNSS receiver on it. So this one, I think it's all driven by this particular group of we kind of missed it because we don't have any sensors in that area, but there are sensors in GNSS.
Mm-hmm. Okay. This is really awesome. Things that can be worked on in detail at some point. Like you said, we need CONGA, and I'm happy that you are here, part of our leadership now, that to bring CONGA to reality, where we can have enough distribution, enough statistics to actually study these things. We see some things over the South Africa, but we have larger land mass over the African sector around the same region. We could study very detailed analysis and see in detail what is actually going on in all of these things over the African sector, particularly when it comes to electrodynamics, plasma electrodynamics. So yeah, any question? Is there any other question that we have? Today, I think we have the privilege of having all our collaborators, not all of them, but we are working actively on submitting a proposal to CONGA, and both group are here. The LDI group, Lowell GIRO International. They are specialized in development and design of instruments, so they are helping us as well. They are collaborating with.
Yes.
Yes.
Sorry. Candles.
Okay, I think that's not for us. So we are happy to have everybody here on this platform, and I want to also specially thank Dr. Ivan again, and also Giorgio that made all of this, all of the process possible. It wasn't easy to get this time from, from Dr. Ivan, but we made it happen anyways. So we're gonna make it happen again, Dr. Ivan. These
Okay.
are fantastic results that you have here. It's a CONGA-like result, everything that we want to see on this platform. So with that, if there is no any other question, is
Can I
there?
just make a comment, Jonah?
Okay, go ahead.
I think most of these efforts, they came from from the need to understand the structure of the ionosphere, because from the past decades, most of the GNSS based studies, they only rely on these understanding of the ionosphere as a whole plasma region. And of course, the GNSS DC is an integrated value. It's not like a measurement or in situ, just like the swarm and cosmic data as we saw in the last presentation by Daniel, right? And the maxima here is try to understand the structure of the ionosphere. For example, the top side TC, bottom side TC, mid length TC maybe. So trying what's the word, to isolate plasma sphere, maybe using different techniques, just like the Faraday rotation, that we know that the GNSS from the Faraday rotation doesn't consider the plasmaspheric contribution because of the sensitivity of it to weak geomagnetic field. So this is the target of all these data combination, data fusion. How can we understand the structure of the ionosphere, not based on the whole plasma region as the TC, as the integrated measurements, but in the multi-layer components of the ionosphere, and that this is how I arise these GNSS and ionosonde and LEO satellite data fusion techniques that will help us to understand and see it better.
Awesome. Yeah, thank you very much for that highlights, Giorgio. So,
hello, Jonah.
Yes, please.
Yeah, sorry. I just want to chip in one or two things.
Okay, go ahead.
Not not really related to the topic on hand. I just wanted to. I've not been attending the seminar for a while now, due to I've been on official assignment for the university. But I'm promised to just go through all the presentations. Right now, I'm even on call for an official assignment. So I'll be going offline right now, then I will contact you later.
Okay. Sounds
good.
good.
Thank you so much.
Yeah, sure. No problem. Thank you very much, Dr. Emmanuel. I appreciate that. And I think we should let everybody go. We are sorry for taking 10 or 12 minutes of your time away from the planned time. But if you agree with me, this is a very important discussions that we have on this platform. And I look forward to seeing you again in our next meeting in July or June, sorry, in June. So we have a special guest speaker that is coming from Brazil. And he has been doing a lot of work on equatorial ionosphere. That is spread F. Is it spread F?
No, it's just sporadic layers. And spread F, of course.
Sporadic E layer. I know she's a specialist on sporadic E layer. So if you want to learn more about that topic, join us next month with Dr. Lysa. All right. So thank you all very much again, and I will see you next month. Thank you.
Thank you.
Bye-bye.
Yeah, thank you, Dr. Hickman. Thank you so much. That was great.
Bye. I'll talk to you later.
Yeah, bye.
Yeah, you know how to find me.
Yes.